Hello class, today what we're going to talk about is simplifying exponent and radical expressions with variables. So in the previous two lessons we spent some time simplifying exponent expressions, then we simplified radical expressions. Now what we're going to do is we're going to simplify expressions with radicals and with exponents, and this time they're going to have variables in them. So they act a little bit different, but not really a whole lot. And they're sometimes easier, but we'll take a look. So here we have the cube root of 64 y to the 6th. And we want to simplify this. What we're going to do is we're basically just going to break this up. Cube root of 64 times the cube root of y to the 6th. And, well, 64, that's 4 cubed. So we have the cube root of 4 cubed, so that's just 4. And the cube root of y to the 6th, that's the same as y squared cubed. 2 times 3 is 6. So the cube root of y squared cubed is y squared. Now another way you can look at this is you could take this radical and change it into an exponent. Okay, write it in exponential form instead of in radical form. So where did I put that? That's right over here somewhere. There it is. Alright. So the cube root, that would be an exponent of 1/3. So we have y to the 6th raised to the 1/3, and when you raise a power to a power, if you remember, you multiply the exponent. So 6 times 1/3 is 2. So we have y squared. And so that's another way you can get this y squared. And a lot of times I think it's easier to change it into exponent form instead of radical form. All right. You can see how they all go together better that way. If they're all the same thing, all radicals, all exponents, it just works a lot better, in my opinion. So let's take a look at b. Here we have the 4th root of x to the 4th over y to the 8th. Now remember, if we have this, we can break that up. 4th root of the numerator, 4th root of the denominator, right? So the 4th root of x to the 4th over the 4th root of y to the 8th. Well, the 4th root of x to the 4th, that's absolute value of x. It's not just x. Now this is always going to be positive because anytime you take anything and raise it to an even exponent, you're going to get a positive answer. And so you're taking the 4th root of that, you're going to have a positive answer. And it's not just going to be x, because even if x is negative, this is going to come out as being positive. All right, so you got to put the absolute value of x. That's a little bit thing that can mess you up. You got to pay attention to that. Now for the numerator, the denominator, y to the 8th, well, that's y squared to the 4th. So hey, the 4th root of something to the 4th, that's going to cancel out, just be y squared. Or you can take this and change it exponentially. The 4th root, that would be to the 1/4 power. So we have 8 times 1/4, which is 2. Right. Another way to look at that. Now here is where the real fun is. All right. So we have the 5th root of 4, 8 to the 8th, b to the 14th, c to the 5th. And we want to simplify this. This is a lot of exponents in there, and so we want to get as few exponents under the radical as we can. And what we really want, we want there to be, since this is to the 5th root, we don't want anything in here to be perfect fifths, right? Because those can come out. Well, 4 doesn't have perfect fifths. What we're going to do is we're going to split out all of the perfect fifths. So that means if we have a to the 8th, well, a to the 5th is inside that, right? This is a to the 5th times a cubed. So there's a perfect fifth right there, a to the 5th. b to the 14th, well, that's b to the 10th times b to the 4th. b to the 10th is a perfect fifth because 10 is divisible by 2, or by 5, right? And then c to the 5th is quite obviously a perfect fifth. It's got the 5th right there on it. All right? So then we're going to simplify each one of these. Well, 4 to the 5th, that's just going to stay 4 to the 5th. All right? But this, a to the 5th, the 5th root of a to the 5th, we're going to pull out all these perfect fifths. The 5th root of b to the 10th, the 5th root of c to the 5th, which leaves us with the 4a cubed and b to the 4th. Well, since these are all perfect fifths, we're just going to take the perfect fifth of this. So 5th root of a to the 5th is a. 5th root of b to the 10th is b squared. 5th root of c to the 5th is c. And this is going to stay the way it is because that doesn't simplify. So this is our answer right there. B. Well, our problem with B is that we have radicals in the denominator, and as you know, we're not allowed to have that, so it's not simplified form. So we need to get this to be a perfect cube. Y to the 8th is not a perfect cube. So how many more y's do we need in order to make this a perfect cube? Well, we want this exponent to be a multiple of the index. So 9 would be a perfect cube. So I need one more cube root of y. So that's what we do. We take the cube root of y to the 8th times the cube root of y, and that gives me one more cube root of y, which is going to give me a total of cube root of y to the 9th. Right? Now remember, anything you multiply the denominator by, you've got to multiply the numerator by the same thing. So we're going to have that. So we have cube root of y to the 9th. We have x cube root of y on the top. This can't simplify that. But this, the cube root of y to the 9th, is y cubed. Right? And this is a lot like raising a power to a power. If you have a power in a radical, instead of multiplying the exponent times the index, we're going to divide the exponent by the index. So 9 divided by 3 is 3. Okay? So let's take a look at C. Again, take these piece by piece by piece. Start with the numbers, then move on to the variables. So 14 divided by 2, 7. Now here we're dividing power by a power, right? So x divided by x to the 3/4. So we're going to subtract your exponent. So that's 1 minus 3/4. All right. For the y's, we have y divided by, no y's down there, so that's just y to the 1/3. And then we have our z's. Well, there's no z's there, but we do have a z down here. We still have to take this and subtract it. Okay, so this is basically like the z to the 0 power. And since this is on the numerator, it's going to be negative. So we have z to the negative z, or negative 6. All right? Because remember, anything on the denominator, it's a negative exponent there. And then we simplify this. 7 is 7. 1 minus 3/4 would be x to the 1/4. Y to the 1/3 is just y to the 1/3. And z to the negative 6, well, a negative makes it a positive. So z to the positive 6. All right. All right. Let's take a look here. So now we're going to be adding these, and they're variables. So just like any other variables, you can only combine them if they are like terms. All right. So here I have the square root of y and the square root of y. Those are both the square root of y, so we can combine them. Got 5 square roots of y, 6 square roots of y. You add them up, and that's 11 square roots of y. Not a big deal. Over here, though, notice these are not like terms, are they? Right? We have cube root of 2z to the 5th and cube root of 54z squared. Those aren't the same thing, so we can't combine them. However, this can be simplified. So we need to take a look at that. And where did I put it? There it is. I'm just going to take this term right here. So first, I'm going to split up that 54. Okay, and what we want to do is pull out perfect cubes. And if you can see those, great. If not, you can just start factoring. So factors of the cube root of 54 are the cube root of 2 and the cube root of 27. And 27, that's a perfect cube. All right. So the cube root of 27 is 3. So this turns into 3 cube roots of 2. Now we still got that z there, so we've got to bring that down. So this is 3z cube roots of 2. Okay, so that's where this comes from. All right. And we still got z squared in there, which for some reason I don't have here. So we've still got the z squared, so there's z squared. Now here, cube root of z to the 5th, well, z to the 5th has a perfect cube in it, right? It has z cubed inside there. So we can pull z cubed out. The cube root of z cubed is z, which leaves me with 2 z's, so z squared. Now we have the cube root of 2z squared, the cube root of 2z squared. We have 12 of them, 12z here. We have 3z there. We're subtracting them. And we end up with 9z cube root of 2z squared. All right. The last one, I want you to work these out on your own, pause the video, then come back and see how you did. All right, let's see how you did. There are the answers. So let's take a look at this. Number 13. All right, so we're going to cube root the 27. We're going to cube root the 9, the q to the 9th. All right, cube root of 27 is 3. Cube root of q to the 9th, well, you can either divide the power by the exponent, which comes out nice like this, or you can change it both to exponential form, so 9 times 1/3 is 3 there. All right, so number 14. Here we go. So there's, remember, if we have the cube root or the fifth root of the entire thing, we can take the fifth root of the numerator, fifth root of the denominator. And I split it up and made it into exponential form so we can see the multiplication, or you can do it as division. There it is. Number 15. 15 is a bit long. So first, we'll take our original problem, and I broke it up for you so you can see this as each individual piece. So 6 divided by 3, x divided by x to the 1/2, y to the 3/4 divided by y to the 1/2. And since we're dividing, we're going to subtract our exponents, and it just turns into this. All right. You could write it like this, but that looks kind of weird, and so exponential form is preferred on that. All right. Number 16. Yeah, people are wanting to come in and get to class. Number 16, we need to take this, get these into like terms, so this needs to be simplified. And so here it is. First, I'm going to rewrite the 9 as 3 squared. Now, the square root of 3 squared is 3. W to the 5th, well, that's W to the 4th times W. Well, the square root of W to the 4th is W squared, and this W is still left underneath it. Here we have W cubed, which is W squared times W. Square root of W squared is W, so I've got W times W times square root of W, or W times W is W squared. Well, hey, look, these are both have W squared times the square root of W, so they have like terms there, and we can subtract them, and there it is. All right. Hopefully that was helpful, and I will see you next time.